less than n. So this is kind of going to be, if you imagine a three-dimensional graph of your p positions, this is going to be everything that lies in the n by n cube near the origin. How many p positions are in there? And what we found is that if you take that n by n cube and you double it over and over again, eventually what's going to happen to the number of p positions is it's just going to approximately multiply by 4 each time you double. So the number of p positions in this cube of size n 2 to the k, as k goes to infinity, is going to converge to, divided by n 2 to the k squared, is going to converge to a non-zero constant. I couldn't have just taken it as n goes to infinity. It's important that k is an integer, and I'm only doubling the size. Right? We saw period 2 scale invariance. Remember, there was all those waves. We didn't have general scale invariance. We couldn't multiply it by arbitrary amounts. We could only multiply it by powers of 2. So what this says is if we multiply by powers of 2 over and over again, that picture that we saw when we doubled the size of the thing, if we repeatedly double the size, it's eventually going to converge. But I'm not saying all the details are going to converge. I'm just saying that the number of p positions inside that cube is going to converge. All right? So fact, number of p positions, it's not just the number of p positions converge, everything's converging. I don't know how to prove it. We can verify this with the computer, and it seems to not be changing very much at all, but it's still an open problem as to find a proof that these actually do converge with all the little details too.
Can you estimate the constant?
You can't estimate these constants very well. I mean, you can estimate the constant just by repeatedly doubling and seeing what happens to it. But in general, the constant is going to be, depending on what your n value is, it's usually going to be mostly monotonically increasing or decreasing, and it's going to have a lot of room where it could decrease by quite a bit. The way that my proof works is that we kind of have this potential which says how much it can change, but it never actually reaches that potential. So if you try to estimate the constant, you can get a good estimate, but you'll never be able to prove that it's not going to later just like jump by a whole bunch. So we can't rigorously estimate this constant in any way. All right, so to prove this, I'm going to I'm going to define a set that is going to have properties similar to this pi of n thing, but it's going to be slightly different. So I'm just going to define this set. Let S be the set of ordered pairs, x, y, such that there is a p position of the form x, y, z, with x greater than y greater than z. So if you take S and you intersect it with the square, by the square near the origin of side length n, that's going to be approximately pi of n, right? Because we don't care about the order of our piles. So if you take S, you take the square near the origin, it's just going to be points x, y, such that there's a p position of the form x, y, z, but all three of these coordinates are going to be less than n. So S is going to be approximately pi. There's a little bit of just differences when you have positions of the form x, x, 0, because you count them twice or don't count them or whatever. But asymptotically, S and pi are going to be, the area of S inside a square of side length n is going to be mostly equal to pi of n. All right, so let's see what this picture, what is going to be our set S. So our set S is going to be positions in which, first of all, x, comma y with x greater than y. That means we're going to be below the main diagonal. And y is going to be greater than z. So z is going to be small. Remember z is being small corresponds to a blue color. So we want things that are to the right of the main diagonal and have a very blue color. So it looks kind of like this. It turns out that this operation, this restriction exactly tells us what positions are inside this big central beam, or half of this big central beam. So we can kind of rigorously define what this big central beam is. That big central beam exists, and it's 2 copies of S. All right. So because of this, my result is basically saying that if you take these pictures and you double it over and over again, and you scale down, the area of this thing, the area of the big central beam is going to converge. Right? That's the main result. So I'm going to show you a proof of this, and this proof is going to be long, but this proof is going to be very helpful for understanding why this is true. So here's what we're going to do. We're going to say that the function, y equals f of x is the curve on the lower boundary of x. So this thing right here. That's y equals f of x. So here's a property of y equals f of x. F inverse of x equals 2 times f of x. So here's why that's true. If we take a look at this graph, what is f inverse of x? Well, f inverse corresponds to reflecting over the main diagonal. So f inverse of x is this top boundary of the big central beam. All right? So if we want to show that f inverse of x equals 2f of x, we have to show is that this height is twice this height. If you fix an x coordinate, say we fix x to be 600, and we go up to the bottom of the central beam, and then we go up the same distance, we'll be up at the top of the central beam. All right? So that's what I want to show right now. All right, so why is this true? Well, say we fix our x, right? Say we say x equals 600. Well, what is the distance to the bottom of the big central beam? Well, what do those points have in common? Notice that all of these points have x is greater than y. And the central beam was points where z was less than y. So in all of these points, z is also greater than y. So these points from the bottom to the bottom of the central beam are exactly the points where your y coordinate is the lowest of the 3 coordinates, x, y, and z. What's the distance from the bottom of the central beam when x equals 600 to the top of the central beam when x equals 600? Well, our central beam, the bottom half is the point where x is greater than y is greater than z. The top half is the points where y is greater than x is greater than z. So our central beam is going to be exactly the p positions where z is the lowest coordinate of your 3 coordinates. So the number of p positions where y is the lowest coordinate, and the number of p positions where z is the lowest coordinate, these two have to be the same because everything's symmetric. All right? So because these two things have to be the same, we know that this distance equals this distance. So the distance to the top of the big central beam for fixed x is twice the distance to the bottom. So f inverse of x equals 2 times f of x. Okay? So now just a little arithmetic. 2 times f of x equals f inverse of x. And we're going to apply f inverse again, and then apply f. Same thing. So f of f inverse of x. All right. And now what we're going to do is we're going to take that middle f inverse, this one, and we're going to replace that with 2f. Right? We can do that. So we get f of 2 times f of f inverse of x. And then that inner f of f inverse of x is just x. So we get f of 2x. So we get 2 times f of x equals f of 2x. All right? So that's your period 2 thing, right? That's where it's going to come from. And the rest of it is just going to be calculus. I'm not going to walk through all of it, but basically we can find this area, which is what we're trying to find. And to find this area, we use f, and we just integrate. And when you integrate, it turns out that, oh, when you double your value, it's going to multiply by 4, which comes from this property. I don't need to go through the calculus. So it seems like a nice proof. Doesn't work. Any guesses as to why it doesn't work?
When you're talking about the symmetry, there could have been those like holes from the forbidden positions.
Our forbidden positions, I didn't say this, but our forbidden positions were completely symmetric. Symmetry is not going to be the problem. You might say that, oh, this is continuous, and we really have this discrete thing, and maybe there's a problem there. Turns out, if you look at it, you can write down this whole thing discrete too, and it'll still work out. But that's not as easy to see, so that's not the problem either. Here's the problem. This boundary that we've been talking about at the bottom of this region, it's not really there. We have holes in our set S. We have holes in our big central beam. It would be nice to say, oh, these holes are going away. Eventually the holes will be gone, and then we can apply our analysis. Not true. The holes stay. The holes stay forever. We can say, oh, well, maybe the holes don't get very big. Not true. The holes can get arbitrarily big. Holes cause a lot of problems. This proof would be probably 2 pages if it weren't for these holes. And instead, it's like 20 pages because we have to deal with where all these holes are. And
But the idea of the proof is similar?
the idea of the proof is similar. So the idea of the proof, I'm going
So
to
the flawed proof is probably much nicer.
yes, the flawed proof is much nicer. And how the proof works is very much like we take the discrete version of the flawed proof, and it's not exactly right, but we restrict where the holes are, and that's going to help us. So I'm going to go very quickly through the rest of this proof. You're probably not going to get very much of it, but I'll take my last 4 minutes to go very quickly through a sketch of this proof. All right, so I'm going to define B of x and y and R of x and y to be inside our set S for a given point x, y. It's the number of points below x, y and to the right of x, y respectively. So if we take a point here, R is going to be how many black things are to the right, and B is going to be how many black things are below. Okay? Lemma, for sufficiently large n, R of n comma n plus 2b of n comma n plus 1 equals n. I'm not going to prove this. Trust me, it is exactly the discrete version of what I gave you with the flawed proof. All right? Another lemma. If ever you're in a point that's not in S, then B of xy has to be greater than or equal to R of xy. So if we go back to our picture of S, that's saying when you have a hole, there has to be more points below it than there are to the right. Okay? And this is our restriction of where the holes can show up. The holes have to have the condition there are more points below them than there are to the right. All right, I'm not going to prove that. Then what I'm going to do is I'm going to set up a sequence of sets, S sub m, and I'm going to define these sets as follows. I'm going to, for a fixed m, here's our m value. I'm going to take our S with holes in it. Everything in here, there are going to be some holes in here. If they're in this region, right, this is where I'm breaking up the regions. If they're in this region, I'm going to fill the hole by taking stuff below it and pushing it up. If they're in this region, I'm going to fill the hole by taking stuff to the right of it and pushing it to the left. If I'm in this region, I'm going to I'm not going to do anything with this region. What I'm going to do with this region is I'm going to recursively define it in terms of these regions to have the period 2 scale invariance. So I'm going to define it so that it satisfies our scale invariance that we wanted. So that's going to be our sequence of set SM. This is the properties that I just said. So now I have a lemma, and it's going to say that for sufficiently large m, there's going to be a bijection from Sm to Sm plus 1 in which all of the points move in the same general direction. Right? They must satisfy these inequalities. So when I move points, I'm going to take my sequences of Sms, and I'm going to let m increase. As I move points, I'm only going to move points in the same general direction. All right? And what this is going to do is this is going to make me able to set up a potential function. So I'm going to assume that it doesn't converge. There's going to be an open ball where it goes above it, below it, above it, below it. And so every time I go from above to below, sorry about that. Every time I go from above to below, I must mess with a potential function by a certain amount. And I'm going to say, okay, this potential function is going to start out to be, it's going to start out finite, and because all the points are moving in the same direction, as I move the points in my sequence of SMs, that potential is going to decrease. It can only decrease so much, so eventually the areas of the SM, the areas are going to converge if you're looking at the SMs, but the SMs are going to converge to not exactly S, but S with the points all shifted up, right? If you let M be high, we're just going to shift the points up in S. So that's the general idea of the proof, and it's a lot more complicated because we have these stupid holes. And that's it.
Thank you very much. Scott, be glad to answer the question in private, but then make a comment that I was given a PhD for this, and it was done while Scott was an undergrad, right? It was sinusoids in undergrad. And for me, it's better than many PhDs that I've heard on your comment. Thank you very much. Thank you, join us for dinner. Please let me know.